Hey everyone, welcome to Module 8. We are rounding out our tests. We only have 3 more, actually 1 more after this week, so we're almost there. This week we're going to be talking about one-way and two-way repeated measures ANOVAs. So last week we talked about independent ANOVAs when we had between subject factors or between subject independent variables. This week, repeated measures is referring to within subject factors or within subject independent variables. And I loved this office meme where this is probably what you guys are thinking now, so I just wanted to stop. But we're almost there, so keep pushing. You're doing really great. Let's take a look at our decision tree. So we've really knocked out a lot of stuff on this tree so far this semester. This week we are focusing on the within subject pathways. So basically all of this top part is the same as last week. And then all we're changing is the type of independent variable. So if we have a single within subject nominal independent variable with 3 or more levels, that's where we use a one-way repeated measures ANOVA. If we have 2 within subject independent variables, that's where we use a two-way repeated measures ANOVA. In our flow chart, if we want to look at it this way, last week we had focused on independent ANOVAs. This week we're looking at repeated measures. So the same thing applies when we're looking at two-way ANOVAs, where you have to have at least 2 levels of each variable. But when you're doing a one-way ANOVA, you have to have at least 3 levels in order to do all of our comparisons appropriately. The goal of an ANOVA is still the same, so this is pretty much a repeated slide from last week, right? So again, ANOVA is the test that we're running. It's the analysis of variance between groups, and we use it to determine cause and effect. So how does a single or multiple independent variables affect the outcome of a dependent variable if they affect the outcome at all? And the major difference, again, between a one-way and a two-way is the number of independent variables that you have in play. Or in a two-way scenario, if you're also interested in the interaction between the 2 variables, you would also want to run a two-way for that reason. Now, for repeated measures ANOVAs, we're still calculating an F-Statistic. We do calculate it slightly differently than we did for when we had between subject variables. To calculate our F-Statistic for a repeated measures ANOVA, you'll see our table here is a little bit bigger than our independent samples ANOVAs. So up on top, we have a row for our conditions, or the treatment or the effect, the factor that we're comparing. To get the sum of squares for the condition, you guys don't need to know how to calculate this, but I've added in the notes what each sum of squares is actually calculating. So the sum of squares for our conditions is very similar to the between subject the between group comparisons sum of squares for independent ANOVAs, where we're looking at the deviation of each group's mean from the grand mean. And the grand mean is kind of like the mean of all of our data points. For the sum of squares of subjects, that's going to be looking at the deviation of the mean for each subject's measurements from the grand mean. So because we have a within subject factor, we have people being measured more than one time. So we can average all of their values that we collect for the dependent variable, and then do the mean of that value minus the grand mean for all of our data points. I'll skip over the error sum of squares really quick because the total sum of squares, whoops, I didn't mean to do that. The total sum of squares is, we can actually calculate this. And we do that by looking at the deviation of each data point from the grand mean, so each individual measurement. And we square all of these, sum them up together. That's how we get our sum of squares. Now, our total sum of squares is looking at the total variation for the treatment or the condition, plus the sum of the variation of the subjects, or sum of squares of our subjects, plus the variation that we have in our error values. So once we know the sum of squares for our total, the sum of squares for our subjects, and the sum of squares for our condition, we can rearrange this equation on the bottom to end up getting our sum of squares of our error. Our degrees of freedom are going to be fairly similar calculation, at least for the conditions portion. So again, conditions is kind of similar to our between group comparisons for an independent ANOVA, where we're looking at the number of groups. So that's what T represents, is the number of groups or number of levels of our independent variable, minus 1. The sum of squares for our subjects is just the total number of people we've collected, minus 1. Our degrees of freedom for our error. This error row is actually also similar to our within group comparison in our between subject or independent ANOVAs. So conceptually it's similar but calculated differently. So here we're going to take the degrees of freedom of our condition times the degrees of freedom for our subjects. And that's how we get degrees of freedom for error. Our total degrees of freedom is exactly the same as our subjects' degrees of freedom. So that kind of gives us the first half of our table, a little bit more than half. To get our mean squared, it's the same calculation that we did last week, where we take the sum of squares divided by the degrees of freedom of the respective rows. So we get a mean square for condition, a mean square for subjects, and a mean square for our error values. We then can take the mean square of our condition divided by the mean square of our error to get our F-statistic. This is going to be the F-statistic for the differences between the groups. So this is the F-statistic we're really concerned about. That's the one that we have the p-value reported for. There's also an F-statistic that can be calculated for the subjects, which we just do the mean square of subjects divided by the mean square of error. This F-statistic is more or less telling us if there are significant differences within our subjects, which we're not always super concerned about, because more or less we want to see what the differences are between the groups that we've measured as a whole, instead of subjects individually. So that's kind of the table. You will notice in SPSS, though, that only the conditions and the error rows are reported. So you'll see conditions show up as whatever the name of the independent variable is for that particular test, and then you'll see a row for error. So subjects and total are gone. Given that information, I will give you guys this whole table to do your calculations on for the activity this week. Just know for the ANOVA table that you get in your SPSS output, though, that you're really looking at the top row and the error row. Again, to emphasize the differences between one way and two ways, we have one independent variable for one-way ANOVAs. And the way that we refer to these when we're using repeated measures is a one-way repeated measures ANOVA. I usually like to abbreviate RM just because repeated measures is kind of lengthy. So if you abbreviate in your interpretations or the activities or quizzes or whatever when we get to tests, RM is fine if you don't want to write repeated measures. When we're doing two-way ANOVAs, we're going to have two independent variables, both of which are within subject factors. So we could call this a two-way within ANOVA, a two-way repeated measures ANOVA, or factorial ANOVA, since it's part of the factorial ANOVA branch. Or we can also use the level notation like we did last week. And I'll give you an example of that when we go through our SPSS output example for a two-way ANOVA. But in terms of the differences that we're looking at, we're still going to be looking at the differences of one independent variable regardless of the other one, differences between the second independent variable regardless of the first one, and then also the interaction effect, which is kind of the primary reason why you would want to run a two-way ANOVA in the first place. For our assumptions, they're pretty much the same as last week in terms of our random sampling, our normal distribution with no significant outliers, and the type of dependent variable that we're using. So still a single dependent variable that is ratio or interval data. For our independent variable characteristics, the only thing that's changing is that instead of a between subject factor, we have a within subject factor. So a one-way ANOVA will have one within subject independent variable with at least 3 levels. And a two-way ANOVA will have two within subject independent variables, each having at least 2 levels. Both cases, we're going to have a nominal type of independent variable. Similar to last week, you could also have an ordinal variable as long as the variable is non-parametric. You're kind of set to go. Like SPSS will treat the variables similarly as they are categorized. For our purposes of our class, I'll just tell you, if you know what the independent variable is, it's always going to be nominal. So that's how you can sort that part out. And then we have a new assumption this week, and it is called sphericity. Every time I see this word, I think of Drake and Josh, which hopefully I'm not aging myself, and you guys have seen Drake and Josh. But I don't know if you guys remember, there was like a game that was in the shape of a sphere, and Josh would always be like, "It's spherical." But that's what I think of when I think of sphericity, and it has nothing to do with being spherical. But we test sphericity using Mauchly's test. Another statistical test named after a person who has an interesting last name. So the null hypothesis for this is Mauchly's test is kind of similar to Levine's test in the respect that we're looking at variances and if those variances are equal. The difference, however, is that we're looking at the variances of the differences between all levels of the independent variable. And the null hypothesis is going to argue that those variances of the differences are equal versus the research hypothesis, or the HA, if you will, which would say that the variances of the differences are not equal. So let's dive into this assumption a little bit more, just so you kind of understand how it's calculated and what we're looking at. So I have the null hypothesis repeated here again. This is actually how it's calculated. So we look at the variances between each pair of our independent variables, or independent variable levels. So if I have levels A, B, and C, a 3-level independent variable for let's say a one-way repeated measures ANOVA, the way that I look at sphericity is I take the difference between the variances of each level. And then I say, are the differences of those variances, or the variance of the differences, are those relatively equal to each other? When we run Mauchly's test, there's going to be a table specifically for the test, which we'll go through in our SPSS output PowerPoints. But there will be a bunch of numbers, and then there will be a p-value for Mauchly's test. If that p-value is greater than 0.05, similar to our other assumption tests, that means that we have met the assumption of sphericity. So when you interpret your p-values for sphericity, you can say sphericity has been assumed. You could say the variances of the differences between all levels of the insert your independent variable are equal. So a little bit of flexibility in how you interpret stuff. And then once you determine that you have assumed sphericity, you go to the ANOVA table in the output, and that would tell you there's different rows based on the adjustments that are applied. So you'll use the sphericity assumed row. Now, if we look at our table and we notice that our sphericity test has a p-value less than 0.05, similar to our other assumption test, that means we have violated sphericity. So interpretation-wise, you could say sphericity has been violated, or sphericity is not assumed, or the variances of the differences between all levels of the insert your independent variable are not equal. When this happens, we need to apply an adjustment. So in our our independent t-tests that we've run in our one-way ANOVAs, we've had different adjustments. Usually it's to the degrees of freedom. And so we'll have similar adjustments here. Like the past, you don't have to know how the adjustments work. You kind of just need to know what they're called and when to use which adjustment. So in the table for Mauchly's test, kind of if you're moving left to right, we're in kindergarten. If you're moving left to right, you'll get Mauchly's test results and the p-value. Once you assess the p-value, you say, we've met the assumption, move on. We've not met the assumption. If you haven't met the assumption, you keep going across the table to the right. And there will be a section that's called epsilon, which is basically like some calculated value that's based on certain adjustments. So, and again, statistics and last names. There are 3 boxes under the epsilon portion of the table. Again, we'll go through this in the SPSS output video, so this should make sense once we get there. But when you look at the epsilon value in the greenhouse geyser box, if it has a value less than or equal to 0.75, you use the greenhouse geyser adjustment, which has its own row in the ANOVA table. And that would be the p-value you end up reading for your main effect. If, however, we have an epsilon value greater than 0.75, you would use the Hune-Felt adjustment. Okay. And for all of these blue boxes, each of these is in the main ANOVA table. So that's kind of the nice thing about repeated measures, is that all of your p-values are listed in the same table. The hard part is making sure you're reading the right row, because the p-values won't always be the same. In terms of the interpretations of the p-values in the in the ANOVA for the main effect, they're all interpreted the same way, similar to how our ANOVA p-value versus Welch's p-value are interpreted the same way. So they're all still looking at, in terms of the main effect, if we have significant differences between the means of the groups we've measured. The p-value or the size of the difference is just going to be varied based on the degrees of freedom adjustment that's been applied, if you've met sphericity or if you have violated it. As a note, because it does sometimes happen in this class, if you only have 2 levels of a within subject independent variable, sphericity will not give you an answer. So sphericity is only determined when you have 3 or more levels of an independent variable. If you have 2 levels, then sphericity is automatically assumed as being met. So it'll give you, under Mauchly's test, Mauchly's statistic will be 1, which indicates perfect sphericity. So when you have 2 levels, you kind of just skip past the sphericity assumption and you assume that you've met the assumption for that given variable. This is really only applicable when we have 2-way ANOVAs, just because in a 1-way ANOVA you have to have at least 3 variables, but in 2-way repeated measures ANOVAs, this is potentially could happen sometimes. All right, going into our hypothesis testing, I will tell you now, all of these slides are complete replicates of last week. So that's the nice thing, is you just get more practice with your interpretations. We're not changing anything. So the null hypothesis for the main effect of a one-way repeated measures ANOVA, again, is looking at if we have significant differences between the means of the groups that we have measured. The only difference, and I forgot to change that. I will change that on your version. But we are essentially looking at one sample of people who have been measured multiple times. So if you think about maybe we're trying a new intervention and we want to see if the effects of that intervention are retained over time. So maybe we take a baseline measurement before we've applied any of the treatment or the intervention, and then we take another measurement after 2 weeks and another measurement after 4 weeks. So we have 3 different dependent variable measurements at 3 different points in time, and time would be our independent variable, right? So the 3 levels of that would be baseline, 2 weeks, 4 weeks, and we're trying to see if there are significant differences between each time point, right? So in that respect, for the null hypothesis, it's the same as one-way independent ANOVAs, but we would read that as the independent variable, which for my example would be time, has no significant effect on whatever we measured. Okay. The research hypothesis would be the exact opposite of that and would say that we do have a significant effect. You could also kind of vary your interpretation by saying there are no significant differences in the dependent variable between the means of samples A, B, and C, or between the groups of whatever your independent variable is. So you don't have to stick to this notation, but I know, like, I provide templates for you guys so that it's kind of just a plug and chug of your variables and you move on with life. All right. So when we determine if we have statistical significance, we're going to be using the exact p-values that SPSS gives us. The interpretation of these p-values is the same as for one-way independent ANOVAs. So if we have a p-value greater than our alpha, or 0.05, we accept the null hypothesis, and we end up arguing that the independent variable has no significant effect on the dependent variable. If, however, we have a p-value less than alpha or less than 0.05, we reject the null hypothesis and say there is at least one significant difference between at least 2 groups of our independent variable. In which case, when this happens, you all know we have to check post hocs or pairwise comparisons. In repeated measures ANOVAs, these show up as pairwise comparisons for all of the tests. Or at least that's what they're called in the output. So kind of continuing on the post hoc thread, let's say we had a significant difference between our time points from my example. Again, these are basically like t-tests where you're comparing 2 means of 2 levels of your independent variable. And t-tests, null hypothesis, where that you had no significant difference between the 2 groups, right? So again, same interpretation that we used last week, which is so nice, right? Again, these numbers in here are not separate independent variables, rather they're indicating the levels, right? So 3 levels for this particular example. So we would look at if there are differences between the means of level 1 and level 2, level 2 and level 3, or level 1 and level 3. And then based on the p-values that you get for each of those, that indicates what your significant pairs are and what your non-significant pairs are. Okay. Again, for our interpretations, if you get a p-value greater than 0.05, there's no significant difference between whatever levels are flagged as not significant. And if we get a p-value less than 0.05, we do have a significant difference between whatever levels. So again, the number or the pound symbol is representing the level of whatever the significant pair or pairs are. Now, when we look at a two-way repeated measures ANOVA, and again, I'll change this on your guys' slides because that was a copy and go. We're still looking generally at the same thing, we just have within subject variables instead. For two-way ANOVAs from last week, you recall we had three main effects, right? One main effect for independent variable A, regardless of independent variable B. One main effect of independent variable B, regardless of independent variable A. And then we also have our interaction effect, which I have on the next slide. Okay. But when we're interpreting our main effects of each independent variable separately, we still are arguing a similar null hypothesis as if we were looking at a one-way repeated measures ANOVA. So we're saying that whatever that particular independent variable is, it has no significant effect on the dependent variable. Okay. And in this case, again, we would be looking at the groups that we have measured, specifically the dependent variable of the groups we have measured, or the mean of the dependent variable measurement. For the interaction effect, again, similar, and I'll change that, and I'll change that. For the interaction effect, we are looking at, again, the levels of independent variable A within the levels of independent variable B. So when we get a significant interaction, we would say that there is a significant interaction, or if we get P is less than 0.05, we say we have a significant interaction between the two variables. The null hypothesis argues there's no significant interaction, right? And then we do all of the syntax adjustments, and we can compare each independent variable within levels of the other independent variable, and going two different ways. So when we interpret these, it's same thing. You do a stepwise process, figure out what the main effect of independent variable A is, determine if it's significant or not. If you have a significant effect of that independent variable, or when we get P is less than 0.05, then you have to run your pairwise comparisons. And if you have significant pairwise comparisons, those are your significant pairs. Okay. So the main effect p-value just tells you if there potentially are significant differences or if there are not. And then pairwise comparisons tell you specifically where the pairwise, or which pairs are significantly different from each other. But you only look at these if you have a significant p-value for the main effect. We would do the same process for independent variable B. Okay, so determine if it's significant. If it is, you look at post hoc tests, and then that will help you identify where your significant pairs exist. And sorry, there's a lag. Okay. As far as how the pairwise comparison tables are outlined in SPSS, right? Again, for the interaction effect specifically, the first column will be the level that you're looking at within. So comparisons between levels of independent variable A within a specific level of independent variable B. The way we interpret these is the same as we did last week. And then you could also flip that, where you're looking at levels of B within levels of A. So again, this portion of our lecture is identical to last week, which is great. So we just get more practice this week. Okay, in the next two videos, we'll go over the SPSS process, like procedures on how to run the test, and then go over some examples of how we can word specific interpretations of p-values.